The ancient Greeks possessed a profound understanding of geometry. They could precisely calculate the area of polygons like triangles and squares. Circles too posed no problem for these early mathematicians. However, when it came to calculating the areas and volumes of curved figures, the Greeks found themselves at a crossroads. Their traditional geometric tools seemed inadequate for this new challenge. The Greeks recognized that straight lines and curved lines were fundamentally different. How could one apply the precision of straight lines to the seemingly imprecise nature of curves? This question vexed mathematicians for generations. The solution, or at least a partial one, came in the form of the method of exhaustion. This method allowed mathematicians to approximate the area of a curved figure by inscribing and circumscribing the curve with polygons. As the number of sides of these polygons increased, they would gradually exhaust the area between themselves and the curve. While ingenious, the method of exhaustion had its limitations. It was a tedious process, requiring numerous calculations. Nevertheless, the method of exhaustion represented a significant step forward, a testament to their ingenuity and perseverance. Into this world of geometric exploration stepped Archimedes of Syracuse, a name synonymous with mathematical brilliance. Born in 287 BC, Archimedes was a polymath, excelling in mathematics, physics, engineering, and astronomy. His genius shone brightest in mathematics, where he made groundbreaking discoveries. Archimedes inherited the method of exhaustion but wasn't content with its limitations. He sought a deeper understanding, a way to transcend mere approximation and grasp the true nature of curved areas and volumes. One of Archimedes' key insights involved the use of infinitesimally small triangles. Imagine slicing a curved figure into an infinite number of these minuscule triangles. By summing up the areas of these infinite triangles, Archimedes realized he could calculate the exact area of the curved figure. This concept of using infinitesimals was revolutionary. His work was not just a refinement of the method of exhaustion but a radical leap forward, a glimpse into the very heart of infinity itself. The method of exhaustion, as practiced by the Greeks, relied on a clever interplay of inscribed and circumscribed polygons. Imagine a circle, the epitome of a smooth curve. Now, picture a square drawn inside the circle, its corners touching the circle's circumference. This is the inscribed square. Next, envision another square, this one drawn outside the circle, with the circle touching the midpoint of each side. This is the circumscribed square. The Greeks realized that the area of the circle lay somewhere between the areas of these two squares. By increasing the number of sides of the polygons, from squares to hexagons, octagons, and beyond, they could shrink the space between the polygons and the circle. As the number of sides approached infinity, the polygons would effectively exhaust the space, converging towards the circle's true area. Archimedes took this concept further with his introduction of infinitesimals. Instead of stopping at polygons with a large but finite number of sides, he imagined polygons with an infinite number of sides. His method of exhaustion, infused with the power of infinitesimals, became a powerful tool for calculating areas and volumes, paving the way for the development of integral calculus centuries later. Section 4. The Lost and Found Treasures of Syracuse. The story of Archimedes' mathematical discoveries is not without its share of drama and intrigue. Much of his work, recorded on delicate papyrus scrolls, was lost to history for centuries. The Great Library of Alexandria, home to countless ancient texts, suffered a series of fires and conquests, resulting in the destruction of a significant portion of its collection. Among the casualties were many of Archimedes' precious scrolls. The knowledge contained within them, painstakingly developed over a lifetime of study, seemed lost forever. Fate, however, had other plans. In the early 20th century, a remarkable discovery was made in Constantinople, now Istanbul. A 10th century prayer book known as the Archimedes Palimpsest was found to contain hidden text beneath its surface. Using advanced imaging techniques, scholars discovered that the underlying text contained long-lost works by Archimedes. Among the recovered works was The Method, which provided insights into Archimedes' use of infinitesimals and his mechanical method for discovering mathematical theorems. Section 5. The Legacy of the Mathematical Giant. Archimedes' impact on mathematics cannot be overstated. His work laid the groundwork for the development of calculus, a branch of mathematics that revolutionized our understanding of change and motion. His use of infinitesimals, though not fully formalized until centuries later, provided the conceptual foundation for integral calculus. Beyond calculus, Archimedes' influence extended to physics, engineering, and astronomy. One of the most enduring legacies of Archimedes is his calculation of pi, the ratio of a circle's circumference to its diameter. He achieved this by meticulously inscribing and circumscribing a circle with polygons of increasing sides. With each iteration, he narrowed the bounds of pi, ultimately arriving at an astonishingly accurate approximation. His method showcased the power of approximation and iteration, concepts that would find wide applications in mathematics and science for centuries to come. Section 6. Archimedes in the modern world. Even in the 21st century, the echoes of Archimedes' genius continue to resonate. The concepts he pioneered, such as infinitesimals and the method of exhaustion, form the bedrock of modern calculus. His work on areas and volumes finds applications in fields ranging from engineering and architecture to computer graphics and animation. The spirit of Archimedes, his unwavering curiosity and his relentless pursuit of knowledge serves as an inspiration to mathematicians, scientists, and engineers today. In the realm of integral calculus, Archimedes' legacy is particularly profound. Integral calculus, which deals with areas under curves and volumes of solids, can be seen as a direct descendant of his method of exhaustion. The Riemann sum, a fundamental concept in integral calculus, is essentially a formalization of Archimedes' intuitive approach to area calculation. Archimedes' work also finds modern applications in physics, particularly in the fields of mechanics and fluid dynamics. His principle of buoyancy, which states that an object submerged in a fluid experiences an upward force equal to the weight of the fluid it displaces, is still taught in physics classrooms around the world.